Now the process for simplifying cube roots is very similar. I didn't include this in the original notes, so this is something that you might want to pause the video and write this down or screenshot it. But if you are simplifying cube roots, the process is basically identical. Instead of everywhere it said perfect cube, we change it to, or excuse me, everywhere it said perfect square, we change it to perfect cube. All right, so step one is to determine the largest perfect cube factor of the radicand. So in more simplified terms, what that is saying is, say you had something like the cube root of 192. All right, so you would come in here and ask yourself, okay, what two numbers are going to multiply to give me 192, one of which is a perfect cube? Okay, and so the way that we're going to do that is we're going to go to our list of perfect cubes. Oops, cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed already too high, I think that's 216. All right, so why is that too high? Because that's bigger than our radicand, right? All right, so since we are supposed to be determining the largest perfect cube, it might be a good idea to start with the bigger ones and work down. All right, so 216, of course, that cannot be a factor of 192. 125, that's too big as well. But of course, you could check that on your phone, or excuse me, not on your phone, on your calculator, and just say 192 divided by 125. Yeah, that's not a whole number. That's 1.536. All right, so moving on down the line, 64, let's check that. I'm doing 192 divided by 64. Bam, that's 3. All right, so perfect. All right, so we're saying, okay, well, 192 can be written, again, just copying over that cube root, 192 can be written as 64 times 3. Right, and I know I mentioned this in the lecture video, but just to reiterate, I always write the perfect square or the perfect cube first. It's not wrong to write it the other way, so it would not be wrong to write it as 3 times 64, but it's just going to make the next step easier if you put the perfect square or the perfect cube first. Okay, so now we're going to expand this, separate it using the product rule for radicals, which says that I can separate this into the cube root of 64 times the cube root of 3. All right, and again, don't forget to carry over that cube root every time, so don't turn those into square roots on accident. All right, we know that 64 is a perfect cube. The cube root of 64 is 4. And again, there is a long way that I can show that to you. If you remember the way whenever we first started learning this, this is how I was showing you. Like you could write 64 as 4 cubed, then you would say, okay, a cube root cancels with a cube. All right, so if you like writing out that extra step, by all means, that's fine to do that. All right, so the cube root of 64 is 4. All right, and then times the cube root of 3. All right, and then again, since we've done this in a sort of intentional order by starting with the largest and moving down the line the opposite direction, we really don't have to worry too much about this. But you would look at your radicand and say, okay, is there anything, is there anything that I could split up 3 into? Is there any numbers that multiply to give me 3, one of which is a perfect cube? No, the first perfect cube is 2, and it's 2 cubed is 8, so that's much larger than 3. So this cannot be simplified any further. We don't need to put this multiplication symbol. It's understood if you write a number next to a radical, it's understood that it's multiplication. And this 4 is kind of far away, so I think I'm actually going to erase it and scoot it over a little bit. All right, there we go. And that's it. All right, now the next topic that we talked about with radicals was adding and subtracting radical expressions. So I'm just going to try to make up a question on the fly here. Let's do the square root of, let's do 5 square roots of 2 minus, now let me think, let's do 2 square roots of 8. Okay. All right, so right now, as it stands, there's nothing we can do at this moment because the radicands don't match. Right? In order for you to combine these, the radicands need to match. But there's a little bit of work that we can do over here to this radicand. The square root of 8 can be simplified. Right? So remember, whenever you're simplifying square roots, you want to look at your list of perfect squares. All right, dot, dot, dot. I'm stopping right there at 9 because 9 is already bigger than my radicand, so I know that this isn't a factor of 8. All right, so moving on down the line backwards. 4, is 4 a factor of 8? Yes, it is. You can write 8 as 4 times 2. So this first piece is just going to drop down. 8 becomes 4 times 2. Okay, and again, just drop that first piece down. Then this becomes 2 times the square root of 4 times the square root of 2. The square root of 4 is 2. Right, the square root of 4 is 2, so I'm going to erase that, and that becomes times 2. All right, 2 times 2 is 4, so I'm going to erase this. Boom, boom. All right, that becomes a 4. All right, sorry I had to do all that erasing. I hate to do that, but I was running out of room. All right, and now since the radicands match, right, notice that our little radicands match. We've got a square root of 2 here and a square root of 2 here. So you really just treat those like they're variables. You treat this as if it was something like 5x minus 4x. That would just be 1x, right, or just x. And it's the same thing here. All right, so you're just subtracting their coefficients. 4 minus, oh my gosh, I did it again. 5 minus 4 is 1, so that becomes 1 on the square root of 2. So the square root of 2 does not change. It's just treated like a variable. It's sort of like a common factor if you want to think of it that way. And again, we don't need to put this 1 out front, just like how we don't have to write 1x, we can just write x. It's the same thing here. We're treating this exactly like we would a common, it's treating it exactly like we would a variable. All right, so our answer is just square root of 2. All right, now moving on to multiplying and dividing radical expressions. Multiplying and dividing radical expressions is a little easier than adding and subtracting. It's kind of just a little bit more straightforward. One of the examples I remember seeing on the practice test looked like this. Square root of 5 times square root of 20. Since these are both square roots, you can combine them, and you just combine them into one radical. That becomes 5 times 20 under the radical. 5 times 20 is 100. And 100 is a perfect square. What's the square root of 100? That's 10 squared, right? So a square root cancels with a square, and that's equal to 10. Okay, and then let me show you a little example with division down here. If you have something like, let's use the same numbers, square root of 5 over square root of 20. Right, you can combine that into one radical. So if you are dividing, you can combine those into one radical. That becomes square root of 5 over 20. Right, that would reduce to 1 over 4, right? Yeah, both of those are divisible by 5. So 5 over 20 reduces to 1 over 4. All right, and then you would say, okay, well now I can split them back up. Now, why would I do that? I would do that because 1 is a perfect square and 4 is a perfect square. All right, so the square root of 1 is 1. The square root of 4 is 2. And that's my answer. All right, the last topic that we talked about was the properties of exponents. Now, I've shown you lots of examples of these, so I'm not going to do examples of each one here, but I will talk briefly about each property. So places where you can find examples of these would be in the lecture video, that's for radicals and exponents, as well as the answer key for the Unit 4 practice quiz. So check those two places for some examples. But our 7 properties that we had for exponents were the product rule for exponents. That's where you have something like x squared times x to the third. So basically you've got expressions with exponents and the base matches. Then you can just add those exponents. So that becomes x to the 5th. The negative exponents rule gives us a way to deal with negative exponents, and it says something like x to the negative 2. We can flip that to the other side of the fraction bar to make it positive. The negative exponents rule for fractions says if you have something like 2/3 raised to the negative 2, that you can quickly get rid of that negative exponent just by flipping the fraction on the inside and then changing that exponent to be positive. The quotient rule for exponents is sort of analogous to what we saw on that top property. And it just says if you have something like x to the 5th over x squared, you can subtract. So if you have 2 expressions here with the same base, you can subtract their exponents, and it's always numerator's exponent minus denominator's exponent. These 2 properties, the power rule for exponents and the power rule for products, or excuse me, actually, I didn't mean to group those 2 together. It's the bottom 2 that I wanted to group together. All right, so these 2 are sort of like distributive properties, and it just says that if you have a product inside of parentheses and it's all being raised to a power, then you've got to square each piece, or you've got to raise each piece to that power. And then similarly, if you've got a fraction inside of parentheses raised to a power, you've got to raise the numerator to that power and the denominator to that power. And then lastly, that was the 5th rule there, the power rule for exponents. So I'm looking right here, the power rule for exponents. That's where you have a power to a power. So if you have something like, let's say 2 to the 5th raised to the 4th, right, if you have a power to a power, you multiply them, so that becomes 2 to the 20th. 5 times 4 is 20. Okay, all right, so that's everything that I have for reviewing for this quiz. If you have any questions, please shoot me an email and let me know, and I'll see you guys next time.